I'm glad to see some audience for the last session. My talk is not about the latest development, but still, as you all confronted with some simulations when you are entering into the MEMS field, or even in optical things and so on, you will be confronted with how do I model, how do I simulate those things. So now, actually, this lecture is based on a series of courses that we deliver already some years from IMEC, and I want to show you just a moment. This is based on the Stimesi courses that already run for 6 years. There we have 5 days, so I had to squeeze a lot of information into 1 hour and 40 minutes. Okay, during this course we have hands-on sessions, but I tried to take the essence of the course, but you will see also there is some general information coming also. So, therefore, I won't lose time, so let's go ahead. If you're entering into the MEMS field, people often directly go into kind of simulations or modeling, but I also will spend some time about what is actually, how can you look at the MEMS design work, and there are different views. I also address very shortly, it comes from the Stimesi series, about hand calculations, design space exploration and FMEA, because I still believe that it's very worthwhile to address this before really plunging into software or tools and do simulation. But that's actually the main part of this presentation. You will probably think, oh, I know MEMS, I can do simulations, but there are several, let's say, design paths or approaches, so to really look at the different possibilities in the simulation flow. Not only to look at, let's say, one device, but more and more people are coming with questions to simulate not only the device, but the package, like the previous presenter said, the package is 90% of the cost, but the package will also have, let's say, it will influence also your simulations, and people want to predict how the package affects your device. And further on the package, there is maybe even the full case, or a full, even whatever application, and people will ask you, can you model this, or can you predict how it will affect the functioning of my device? So, I will also address a little bit what I call the difference between the ADA culture, and by ADA I mention what is typically the CMOS culture, people that are grown up and have background in the IC design, compared with, and I call it, or I cover this with the CAD culture, which is typically in the mechanical world. A special case is co-simulation, and for example, these timing devices and gyroscopes, that really have to do the optimization in the both domains, and that's a special case. And one case is also model order reduction. Okay, so start with the different views. Typically, and that's what I liked, MEMS encompasses different physics. And I like always to be confronted sometimes with heat, sometimes with optical things, sometimes with flow. You have the different domains. That's nothing new. You have also different disciplines by which you will be confronted. People working in the process. Sometimes you, let's say, especially if you are a designer and a company comes in the biofield, you have to communicate with them. There are different players. The assembly house, testing partners, you have to speak their language, so you have to understand them. And of course, there are a lot of different tasks. If you're doing a PhD and you have your in-house process that you can develop, okay, you have to do whatever the process development. Sometimes you have to even do your own design kit setup. So it's compared to IC design, there is a design kit, but in MEMS you have to do it all yourself, mostly. Another view is, initially you start from a very high abstract level, and then you can do some hand calculations, and these are tools which you can use for this, what I call hand calculations. One step further, you have some more complex equations, you want to do some iterations, there are some tools that help you with that. And then you can start even behavior modeling, which, let's say, reduces the level of abstraction, and you come to a more detailed level. But there is a further detailed level, and typically this is finite element modeling, finite element tools. I mentioned here some of them which I knew or I know. There, of course, there are many more. Then you have some process modelers or emulators. And in the end, and that's a typical thing in the MEMS field, you have to come up with the masks. So you have to do 2D layout. So what you can conclude is at the abstract level you have general tools or generic tools, but you have to learn more about the specific tools the more you come to the realization or to model the detailed level. And that brings me to the third point of view, which I learned from experience while I was in a company, and actually, and I will repeat it during this presentation, there are a lot of tools, but there is no tool that can do this all. So I learned that I focused, or it was better to focus on the interfaces between the tools, because that allows me to interface with other people and to avoid redrawing or reprogramming some of the information coming from their tools. And if you look at the interfaces in the modeling part, and they have 2D modeling and you have 3D modeling. We have to live with the GDS language, which is standard because we have to make the masks. But in the mechanical world, there exists historically the drawing exchange format from AutoCAD, and most programs have some kind of import to that. So that's an important one which you should put your attention to. There are also 3D interface languages, and one of them is the IGES format. It was a trial to define a standard, but it's not a successful one because everybody had to implement its own standard. And if you have a 3D model, you export it to IGES with one package and you import it into another package. I'm not sure you will get the same shape again. So you have to rely on the code from the 3D models themselves, but that costs you some money extra. On the other hand, you have the languages or the interface languages that describe, let's say, the behavior models. You have SPICE, which is actually the historical language to describe schematics. You have hardware design languages and the analog extension, VGL, AMS. I mentioned MUST because it was with SABRE with Coventerware from Synopsys. And of course, you also have some packages that can read in kind of symbolic language. And the most important one is ASCII, because it allows you to change some scripts, some log files or whatever. So that's very interesting. And one example or exercise I did was we draw all the package that we wanted or that we had, and we looked at what are the kind of connections that exist. I'm not going to detail, but it shows you a little bit the kind of chaotic forest of different tools if you're happy that you can spend the money, but most universities of research centers, they have several tools. Okay. Another view, that is actually what I call the marketing view. Typically, you have some customer and he has an application in mind, and he comes to the foundry house or a research institute which have a certain technology based on physics, and then they come with the question, can you make this? And to bridge that gap, that's actually what I also like, that is the MEMS design phase. And that is a very difficult world. You can publish about one thing, but really to make a product of it and make it reliable, there's a lot of work. And typically in MEMS you have what they call the lock-in of one device, one process. So you have to define a kind of design flow. In this case, the program tools which we had in-house, ANSYS, Control, Coventor. There is some layout tool. It is a standard cadence, but for other people that are a more low-level entry tool, Aledit. I mentioned the exchange between data is very important. You do some finite element modeling. You can do some, from that one, reduced order models, or there are behavior models, and then you can put this information into higher level simulators. I mentioned Simulink, but sometimes you can also implement it in SPICE or in even design, let's say, the hardware design language models. Okay, that was view 5. And actually, I will end with this one. Most of the things depend on the data. That's the easiest one, accessible. There are a lot of tools, but it's how to come to, let's say, how to use that and how to come to the model and the simulation to get out the results. And I want to try to give you some advice. It's just my personal experience. There is no holy grail in that. Another view is a timeline view. Typically there is a MEMS design, but It doesn't stop at tape out. There is the package that you have to include. And often you have to do the qualification, and I'm sure that there will be problems. You have to do phase analysis, which require also do some simulations. And maybe before there is the process development and a first pre-design and a loop. Because the MEMS and the technology are very tightly integrated. And this is how it fits, or how it could fit. Because I have some lessons learned. So initially you have the design, and then you have some test phase, and you have the transfer to production. And then the problems only then the problems appear. And that takes longer. And not all companies will admit it, but most companies, they will, especially in the early years, they had to completely start from scratch again after several years of investment, because only the problems appeared, and then they have to solve them at the device level. So it took a long time. I was in a company making accelerometers for the automotive industry. But I felt not alone, because at that time I had some quotes from very famous people. For example, here from Asian Microsystems. You can read it yourself. Another extract from that thing. And you see that from the first prototype towards the production, 5-7 years. Luckily, this is already some years ago. So maybe it is now between 3 to 5. But still much longer than the production cycle and the development cycle, which people that have, let's say, been taught and grow up in the IC industry, because in 6 months you can come from the prototype to production. Another one, he was a former director of Leti in Grenoble. It says the same, about 5 years. And as you don't do it alone, you need a team, minimum 5 people, something like that. And there's another quote, but it's more specific to the safety business for cars. So the device costs nothing, but you risk a recall. And that can eat away your whole profit of the whole year. So there is very high requirements, but okay, that is maybe only for a certain field. A very generic point of view is, MEMS design, you have a creation phase. You have the idea, that's a nice thing. You're bicycling home and you say, oh yes, that, or you're in a conference and you have a lot of new ideas. And then, phase, you have to verify it. Just some simple calculations. But the same you see coming back in the later phases, you always have to verify your design, your layout by simulating, by modeling. So I will address this loop. But before modeling, let's start with the idea. This comes from a colleague from MEMSCAP, Buzz Hardy. They offer the PolyMEMS, which is the oldest MPW service already. But okay, you can. The idea is simple, but mostly there is a lot of other things behind which is even not clearly defined. So this brings me to specifications. So there's some words to say about specifications. During the Stimesi course we address that. I'll skip it here. And then after the specifications you can start with some hand calculations. Well, it depends. If you are in a PhD or in a company already with many years of experience in a certain subdomain, you don't have to start again with the hand calculation. But if you're a design house, the question can come from different fields, so you have to really dig into the constitutional equations to remember how it is with temperature, radiation, what are the equations, or optical effects. First thing to do some hand calculations before diving into the simulations. And I emphasize this enough. Don't trust the simulation results without having done some calculations before. There is always nice graphs and curves, but you should compare with what you have done in the beginning. That's very briefly. And then the designs exploration, there is no super methodology, but I promote a kind of systematic approach. I will show it in a minute. And then there is the failure mode and effect analysis. Often overlooked. It is mostly required when you have to adopt ISO or QS or let's say quality requirements. And then it's most of the time very boring because it's filling in documents. I want to take the interesting part out of that as an engineer, not only the administration part of it. Let's look at the design exploration. Where do we start? Do you start with the performance specification and then try to find out what area you need and what thickness you need or what length you need? Or you start with the constraint of the area or maximum power? So there is a lot of ways to derive the decision tree in which you define some dimensions. And there is no one clear way, so you have to do it iterative, but maybe you can try a systematic approach. I have to go quickly through that because it's too far. Well, you have to write down all the equations, that's clear. Then there are constraints. Limit, specs, target, parameters, properties, and just interesting to just write down the variables, parameters, properties, and you rank them from little degree of freedom to large degree of freedom. Those that have little degree of freedom are typically physical constants. You cannot change permittivity over there. Second one are the material properties. You can change materials, but they are mostly already defined in the process, so you cannot change then the mass of silicon. And what is most large degree of freedom are those things that you draw out. And then next step is simplify the model, because you will have a lot of interdependencies. Lump variables together instead of length of a beam and a crab leg thing. You can just lump it as a decay, which is a spring constant, or a global mass. Of course, it's not that detailed, but it's at the beginning. You can neglect second order effects, but that's a danger because you have to look at it again later on. And the next step, and that's a little bit the tricky one, you can simplify the constraint, or what I call the inequalities, by kicking out, let's say, some variables. But you have to take into account why you can kick it out. To give you an example, in this case, when A must be larger than B and C, and both B and C are positive, A must be at least larger than B. If I can later show to my customer that it is not possible to reach that requirement in the end, then it will not even be possible with the C. The purpose is to get rid of an n-dimensional search space, simplify the interdependencies, because sometimes you have appearing the parameters in the left-hand side and next time in the right-hand side. And the purpose is to end up with a limited set of functions where you have the large degree design variables as a function of those that you defined before. And then you can make graphs, maybe a two-dimensional graph or sometimes a three-dimensional graph. And then you can have, you can define a fixing order. I will show it in the next thing, and then close the curtains. That will be the second slide after this. What I mean with that. Here is again about the variables which large degree of freedom and those that with little degree of freedom. So I mentioned already, you have the physical constraints, material properties, specifications. You're not going to negotiate that again with your customer. But if you can find out that you have very difficulty it's almost impossible to design such a thing, you can start, of course, negotiating some of the parameters. This was the case of a kind of RF ohmic switch. This is defining the order of the defining the parameters. You can make some graphs. And then you can try to put as much of this information into one or two graphs and then have some criteria. And because they are based on constraints, you can exclude some areas, and that's what I mean with close the curtains. And actually, for a certain project, we had some specifications which are, let's say, the easy ones and the more advanced ones. And in this way, we could clearly prove to the customers that by this correct scheme, We could even demonstrate that it was physically impossible with a certain technology to reach the advanced specs, because there was another curtain that ging, whoops, it moved until here. So then you have a good base to start negotiating again, so that the customer relaxes one parameter, or you can look for different technology. And even when there is some potential, you have already idea where to start the first, let's say, design parameters. Of course, this is a simple thing, but it helps you in, let's say, an n-dimensional space. And I prefer it than just relying on automation. Computer programs will, because they will, if you have a lot of maxima or local minima, you will end up with something which you do not expect. FMEA, think before you start. If you look at the phase of a product in time, initially you spend little money, but the more you evolve during the product development, in the end you have already spent a lot of money, a lot of decisions are fixed, and if you discover at the end a problem, then you're really facing big problems. That goes together with the graph I showed you, that when you are in the transfer to production and then you see really the problems appearing, it's difficult to overcome the inertia to solve the problem here. But actually a lot of companies had to do it in the past. So there are of course some problems related to that. Most of all, it costs a lot. You lose maybe the market window, or your customer is very unhappy. And there is a methodology, failure mode effect analysis. What is it? It is actually, you look for all the risks to improve either a product or a process. More detailed, you look at the potential failures, how they might occur in a part or the full device, and determine the probable effect on all the other parts and on your full thing. It will become clear in the next slide also. So what can go wrong? What are the basic risks and how can we prevent it? So these are actually 3 questions one has to ask. Historically, it comes from the military industry. It was then applied during the Apollo project. And actually it was Ford company in the years of 70 came first with it, because they really faced a problem with their Pinto car, which was a successful car. But because of some accidents and cars really burning to flames, they had a big problem with their image, and then they implemented this FMEA methodology, and it was later introduced in the automotive industry and now adopted in a lot of other industries. For me it was new, because I never learned about it during my studies, only when I was in the automotive company that I learned about it. Then I learned first about the tedious thing, which is the administration. But I want to take out the interesting thing, because it even for a PhD student can help. So it looks at the complete system and the subsystems. So on the parts, the effect on the board and on the other levels. It is something that you do before, so you try to, prevention is very important, reduce the cost, and you prioritize actions. So take enough time to prevent the problems instead of using a lot of time to fix them. That's general knowledge for my grant award. How do you implement this in a kind of systematic approach? Okay, this is repeating the same. I just want to emphasize here that it can be nice because it can be a team effort. And that's also the power of it, because you address knowledge from other people, and there lies the power in this methodology. So the flow, define your system, that's the first step, and make a reliability block diagram. This is actually from the the ISO documents, original documents, but you're free to draw any graph and link the different parts and how they affect each other. What is the purpose of this block diagram is that, of course, it helps you determining when something fails here, what's the effect on the other part. Set up a team, members with various background, and also important that you have a good session leader facilitator. Because the next part is the funny, or the pleasant part. No, not only next, Of course, you have to inform your team about your system. Don't plan a meeting, inform about your product or design. Inform them before this meeting so that they have time to grasp what you're going to do, they have time to digest and maybe think of some problems. Because the team meeting that comes, actually, that's the core work of the FMEA model, is find and document all possible failures and the effect on the system. And that's the funny part. You can think about the most stupid, the most unlikely thing, but that's the power of it. Murphy's law says if anything can go wrong, it will go wrong. Mostly people overlook those things that can really cause problem in the end. That's why you have to address some experienced people, some in packaging, the people in the processing, somebody in the mask making. You have to bring them together. You have to inform them of what you have to do. So it costs you time. It costs all these people time. But it's worthwhile to do it. And for all this failure mechanism, you have to look for the failure effect and you give it a number. And that number is the severity or the impact number. Something can fail and it can not make your product dysfunction. So then it gets a low number. Or when something is really impacting the full function, then it gets a high number. Next step is find the causes and how probable it is. When it is very unlikely to happen, then it gets a low number. When it is surely to be happen, then it gets a high number. And then detection means is the detectable number. If you can detect it easily, it gets a low number. If it's difficult to detect, it gets a high number. Those numbers are multiplied and they give you kind of risk number. There are details. Sometimes you have to look only at the, let's say you leave out the detectability. I'm not going to detail about that. And based on that you make an action plan to either improve some product or design or some step. That's the different steps, and mostly it is implemented in a kind of table. Very simple, the failure mode, the effect, it gets the severity number, the failure cause, occurrence, and the detect, so the controls, detectability, and then you get your risk priority number, which is the product of this one, that one, and that one. You're free to implement it in your own way if you are not required to do it in the official way by quality documents. So in your PhD or research, in whatever, you're free. But the idea is to rank the potential problems, define an action plan, of course responsible and a date, otherwise it will never happen, and then it can be repeated. So it's a living document and a living approach. And one of the interesting things is that the first time it's maybe tedious to document all these problems and to discuss about numbers, but the next time, okay, it's frustrating if you list all these things that can happen, but the next time you can reuse most of these things for a new device. So you actually, everything which is in the head of the team members in a certain way is fixed into documents, and it can help other people. And you can reuse a lot of this material. So, that's about the preparation phase. Okay. I think you grasped the message of FMEA. It's not only on devices. You have the DFMEA, device failure mode and effect analysis, but you also have the PFMEA process. It's also used for software. Maybe you can invent the PhD FMEA. Anyhow, there is a lot of guidelines, you can find a lot on the internet, but I still, let's say, it costs nothing, just time. Okay, enough about this before the design. Now jump into MEMS design. And in my opinion, I still believe finite element modeling analysis is the workhorse. There are a lot of other tools, but still, in the design, it offers you still the most flexibility. So what is FMEA or FEM? Well, I like to compare also again with the IC world, because let's say typically in Europe, a lot of people that enter into the MEMS field have some background. I heard in Taiwan it's opposite, more people from let's say physics or mechanical background enter into MEMS. Anyhow, this comparison is maybe not difficult for you. We have single domain, multiple domain. In IC world, we can actually separate design from the foundry by design kits and so on, but here we have a tight connection between the device and the process. We have interface with the external world, which is reflected then in the need for special packages. But the most, let's say for the designer, different thing, in my opinion, is that in this world we can work with behavior models in a schematic editor, but MEMS, multiphysics, it requires the real physics modeling and the simulation approach. And that is actually requires 3D modeling and meshing. What is this meshing? For people, and sometimes I have to explain to people that are completely unknown to the field, is, okay, I try to mimic the real world with something which is more coarse, like a child can mimic a motorcycle. And one of the nice things I can explain with this is that the smaller the parts compared to the full object, the more accurate you can model the motorcycle. And this is shown in the next slide. So this is a very fine mesh, and it represents this Volvo car very accurately. Example meshes, it's not something from the MEMS world, it exists already maybe 40 years already. What is finite element actually? And with this example of the mechanical domain, I try to explain this. Just assume that you have a kind of sensor, it is already meshed. I'll take some of these elements, I'll separate them, and I just look at one. And just like in physics, where you can describe your forces on an infinite element, we describe now the forces or all the influences on a finite element. So for the mechanical world, I have stresses on the faces, I have maybe volume forces, and due to that, the structure will deform. And deformation will be, the forces will be balanced by elasticity forces. And actually this is written by Hooke's law. Normally for a linear spring this is linear, and now we can actually write it for every node, and we write it for every element. So this gives the full matrix, and this matrix can be solved by mathematical solvers. And from the solution you can calculate depending variables like the stresses and the strains. Very briefly. So, statically, still in the mechanical world, I have this equation, but if I do it on the full meshed model, I have in matrix form, these are my unknowns, nodal displacement, these are applied forces, and this is what we call the total stiffness matrix for a static problem. And in, you can have forces which act on the nodes, on the areas and the volumes like pressure, gravity, thermal. And in general, mathematical people, they describe it in that way. Luckily, you are not confronted with that if you use nice modern tools. COMSOL, formerly known FEMLab, it still allows you to describe your problem directly into this mathematical form. But you have to really dig into the mathematics. The same is for dynamic problems. You see again the linear Hooke's law, but the time-dependent force, a damping term, inertia term, and this equivalent equation, which is not only valid for mechanical things, but also for a lot of other physical domains. So that is a general thing about this methodology. Compare with SPICE. I asked, okay, here with SPICE, if you have followed electronic engineering courses, if you want to solve such a circuit, you can separate it and you can write down, let's say by Kirchhoff laws, every loop or the voltage on the node should be the same, and it is put into kind of matrix, and SPICE, it solves that matrix. Some of that mechanical courses, this is a typical staircase or ladder, simplified in such a model, and in mechanical world they say separate by parts again, and you write down the equations on every part, and because the solution on that part, and of course it should be the same on the node there, and then in this way you also write it down in such a matrix. But there is one big difference, in my opinion. I asked an analog designer, what's the size of nodes or elements of a complex IC circuit, analog, not a digital. And He said, yeah, 10,000 nodes can be already quite challenging. In electrical world, you have 1 degree of freedom, either the current through a branch or the voltage on a node. So you have 1 degree of freedom per node. That ends up that if you want to simulate it, it can be maintained into the memory of, let's say, even the early day computers 10 years ago, and you have a static solution in seconds, and a transient or a dynamic solution maybe some minutes. In MEMS, if you mesh, you easily get much more nodes. You have typically 3D degrees of freedom, X, Y, Z, and if you include some bars or whatever, you have also the rotation of these bars, so you have 6 degrees of freedom, and you easily end up with, let's say, half a gigabyte of memory, and for a static solution it takes you hours, and if you want to do a transient solution, there's a lot of other work, emails you can answer, and then maybe the next day you will come back and you can look at the result of your simulation. So, in order to bring down the simulation time, there exist many techniques and tricks which makes MEMS design an art. What's the typical flow? Maybe not unknown to you, so you're familiar with. In 2D, you design, you have to do the layout, apply material properties. In 3D is the same. You measure it, very simple structure now in 3D, and apply the boundary conditions and the loads. In this case, just a simple cantilever beam, and then you can solve it. And for this one, it is within seconds done, but per complex you have to wait. And if you're lucky, let's say the assembly of the big matrix is okay, but sometimes it crashes already there, and then it starts solving the system, and you get, of course, these nice animations by which the software vendors sell you this software. About meshing, some slides to show you the problem of the mesh density. Assume that I want to mesh this kind of flange with round shapes, and I mesh it very coarsely using 2D elements, triangles. But you see that my corners are not very well represented, or my round shapes. I can mesh more densely, and then you see it improving, but still, well, okay, I mesh further. Now what you can see is that initially I had very little elements or degrees of freedom, and it suddenly increases. So it increases more than linear. You can mesh with other elements. Very simple things are quad elements in the 2D world, and they have sometimes advantage over the triangulars. Like in this case, I can represent the curvature better, and I end up with fewer elements or degrees of freedom. But if I mesh more accurate, or let's say this may be overdone, depending on what you need to simulate, but you can easily see that it rapidly increases. There's another technique, but then you have to do it manually. You see that in this simple case, I separated this area in sub-areas, and I instructed the mesher to do some tricks, and I end up with already a good representation of these curves, and I have also a very homogeneous mesh, and it just takes me 2000 elements. So actually you can see you can save time by doing this, but it's not done automatically anymore. In the 3D world you have the equivalent, but then it's called the tetrahedron, or the four-faced element. You can sometimes use brick elements. In this case, one face was meshed with the quad elements, and it was extruded in the Z direction. And for complex geometries, you can have a mixture of elements. And in this case, I have, let's say, separated the easy part of this volume, which I could mesh with very regular, let's say, 6-faced blocks. And I needed a kind of pyramid to interface the square area with the bottom, with the triangular area of the tetrahedra. And with the tetrahedra you can mathematically mesh any irregular shape. But again, this is done automatically. Some words about the meshing elements. You can have elements which represent a linear change of the unknown property over its side, which we call linear elements. Or you can have an element which have an intermediate node, let's say in this 2D model you have intermediate node, and then it can represent a parabolic change of the unknown property. And then it allows that, let's say here, the smooth change over the different elements, and here you present it piecewise linear. You can have elements that represent different physics, and in this case I have to address a word. Some solvers or some tools, they first mesh, and then you select the physics that are represented by the mesh. Or some tools, you have first to select the elements which represent a certain physics, and then mesh with that element. There are pros and cons between both approaches. Sometimes, and for specialized things, it is better to use elements that represent a certain physics because they are tailored to, so they have some, whatever description makes that, let's say it has an influence on the mesh and it allows them to represent the physics better. So you see here, this comes from ANSYS. You have 2D elements, 3D elements, even bar elements. Some of them represent thermal properties, some of them mechanical structuralists, some magnetic or flow. Let's say in ANSYS there is a whole jungle of elements. And then you also have special elements. Actually I already encountered it, which is the beam element or a bar. I don't want to model the Eiffel Tower with just this kind of trusses. It would be too complex, but I can represent it by a more simple representation. But it still includes the mechanical properties, the cross-section of the full bar. And the same is true for shell elements. Shell elements are 2D elements, but they have degrees of freedom in the 3D world. And they can represent sometimes maybe more layers. So they are typically used to represent the shapes or the hull from, for the car or pipes or even the airplanes. In the end I have an example where I also took advantage of these shell elements in the MEMS world. These are special elements. Okay. There is one thing in MEMS that is very typical. You have different length scales. Mostly if you deposit a layer, it's very thin, but in the X and Y direction, so in the area direction on the wafer, it can be very long. So you have multiple scales. Or sometimes you have slender structures, beams, membranes, or you have a piezoresistor, while you still have a very bulky mass or frame around. And that conflicts with the requirement of finite element that your mesh element should have a good aspect ratio. Otherwise, your solver will not converge. Here are some examples of good elements, and there is no fixed rule for that, and here are some just illustrative bad elements. And you can imagine, for example, if you describe a certain rate of change from here to there, you can miss something which happens here. Or if you have a rate of change from this side to that side, it will, and here, let's say it changes from 1 to 2, and this node converges to 10, the solver will have problems to converge. That's actually very intuitively that I can explain this requirement. And that causes a lot of trouble, because if you, okay, I can illustrate it with this simple example. Assume that you have just a simple rectangle, and I push the button mesh. That's easy, very regular mesh. But assume that I have a very small notch in this thing, and I do with the same settings, I mesh it, I get a very good representation of this small notch, but I have a mesh with a very bad aspect ratio. Sometimes it will not cause you a problem. Thermal problems, they don't suffer too much from that, but other physical domains, they will have a problem in converging. Of course, not on such a simple structure, but on more complex geometries. I instructed the mesher to treat that boundary as one boundary, and then it gave me an homogeneous mesh, but representation of this notch is not good. Which brings me to the following. If this is relevant for your device, you should model it. If it is irrelevant, better kick it out, because it causes you a lot of problem. So when I'm interested in the temperature behavior from, let's say, from this side to that side, whether there is this small notch or not, it will not be important. Of course, I can also mesh with these triangles, and then you see that I can have a homogeneous mesh, homogeneously going from small to large, and representation of the small thing. But you see again that it give rise to enormous larger number of elements, which has an effect on the simulation time. The reason is that the mesh must be contiguous. Go back to here. I can, let's say, have a node here, and of course in the assembly matrix there should be the same solution from the, let's say, the node here belonging to that element. The solution should fit with the node from that element and that element. I cannot have, let's say, a node that just ends in between. Which is not a problem for triangular elements, because you can always reduce the number or increase the number of divisions on the site. But there are tools and tricks to separate small features from the larger so that you can have dissimilar meshes. One of them, I already mentioned it, is partitioning. And the second one is also an example of that. Another way is to make use of boundary contacts. Some software packages call this links and ties. More and more software vendors are helping you by offering you a lot of contact boundaries. But that's a topic on its own. For example, if this is a structure, and let's say the solver, it can maybe interpolate between the solution here and there to find the solution, so and apply that value on the other part, but it's not directly then, let's say these are extra the matrix. It's a little bit more complex then, but how do you apply it? There is a kind of directionality. For example, when you pre-compute a solution here from this side and apply it on the other side, it makes a difference than when you compute a solution from this side and apply it on the other side. It's not in the full matrix solved at one time. Another thing you have to be aware about is that if this is a thermal model, you can maybe nicely have convergence on the temperature, but are you sure that the energy exchange, the heat exchange between both, is respected by your contact boundaries? So you have to treat those things with care. But there are, of course, a lot of type of boundary contacts. Another thing to separate small from large things is what in ANSYS is called submodeling. I took that idea over. So if you're interested in some details here, you can of course mesh everything very densely. But what you can do is a two-step solution. You mesh first coarsely, and then take the solution on the edges of the yellow part and apply it as a boundary condition of only that yellow part, which you mesh more densely. And this is an example of it. This is a case of a kind of old-fashioned bulk micromachined accelerometer in a ceramic package, and we were interested in modeling the effect of the whatever mechanical forces on that package and that feed through, so that on the performance of the sensor. If you know that this is a piezoresistive device, there are features inside, let's say on the micron scale, which should be meshed lower than microns, and that is 2 centimeters. It will, if I measure it in a contiguous mesh, it will cost me a lot of elements. But as the structure inside this mass and springs is so flexible compared to all the other thing, I can neglect it and approach it, let's say, by just the top and bottom cap and the silicon that it needed with, and then I apply my force on this ceramic, and actually the result on the bottom face, so the die attach, I apply it in the subsequent phase on a very realistic mesh of this accelerometer as a boundary condition, and then in the subsequent phase actually, and I can see the effect of this solution on the bottom on the piezoresistors. That is an example of submodeling. Another way, the opposite direction, is supermodeling. Assume that I have kind of problem, let's say that I want to model temperature in here, there and out there, and I'm not interested in what happens inside. I can just pre-calculate the effect from this side to that side, or I can pre-calculate the stiffness in a mechanical domain and the centroid of mass and represent it then in just a simple, let's say, a kind of higher order model, a reduced order model, and then I can combine these elements together. So you see again, two-step approach, and here also a kind of two-step approach. And actually, this shell element and the bar element which I mentioned are kind of super elements. Only thing is that they are parameterized. They are pre-calculated for you, and you can change the dimensions. And actually, yeah, in the following, let's say, becoming more complex, you have the behavior models, which are parameterized models. There is maybe not a finite element model behind, but maybe just a kind of mathematical equation or a lookup table or whatever. And this is what I call behavior models or parameterized models. So you see, from simple elements to more complex elements, they are all available to allow you to simulate. Okay, here have some examples at that time from Saber, Coventerware. They have now another program. And then they are, let's say, like the electronic schematics, they also are represented by a schematic. And actually, Simulink, they also offer kind of building blocks like that. So, first conclusion, the physical design is the most striking difference with CMOS design. And FMA methodology, you have to draw something. Simple geometries can be automatically meshed, but large models get out of memory or take days to solve. So you have to require manual meshing, and there are a lot of techniques to do that. The feature size of MEMS makes it more difficult, and there's a lot of manual input required, which makes the automation very hard. That's why I say meshing is an art. Next I will go to the geometry modeling, and I want to give you an example for gyroscope. Typically, this is a part of a structure which I did 7-8 years ago. If you are in the functional design phase, you can actually, instead of meshing those things, you can represent it by equivalent mass. You get rid of the holes and you apply a certain percentage to the flexibility and also to the mass. This is a part of it, and then you can easily mesh, and you see that I have, let's say, 8,000, 9,000 degrees of freedom for that part. So that was quite easy, but this is not enough for optimized design. If you just make a structure and the functioning, the intended function of a gyroscope is to move like that, but of course there will be modes where it is warped around. The holes, they affect the flexibility in the Z direction. So you cannot apply just an equivalent stiffness anymore. So you really need to mesh accurately. And on this structure, just I tried to do it my best, and I meshed. I get, let's say, even on this is a quarter of the full gyroscope, 300,000 degrees of freedom. This is also the, let's say, at that time we didn't have 64-bit computers, so the memory addressing space was limited. That can cause you problems, but actually that fitted into the memory. I could solve it. But the next generation of this gyroscope, where we try to use as much as possible of the free space, here, this is not the floor plan of a church in Italy, in Rome. This is actually where we filled all unused space. I wasn't able to put it with the same methodology into my memory of the computer. So I had to look for tricks. Now, there's one thing. How do you represent this? In a drawing, it's easy. You just draw, and you draw the holes. But for a layout, it's already different. So I advise people not to make one very long polygon of it, because your DRC checker will choke on it. Your foundry will say, hey, I don't like it. So preferably, people ask you to draw the area around, and in another layer the holes. So that was the way. And also, for if you import that in your 3D modeler, instead of giving your 3D modeler a very polygon 1000 vertices, it will choke. But if you give your 3D modeler the external boundary, you extrude it, and then you make all the holes, extrude it, and you subtract that. But actually, it did not work good enough for my case. So my solution was actually, instead of drawing the edge and the holes, I draw just vertical bars and horizontal bars. Why did I do that? Well, just zoom in. By importing then from my layout tool to my 3D modeler, I could do a kind of Boolean overlap. And then I have a structure which is completely partitioned already. And then for example, if this width was 2 microns and that was, let's say, 6 microns, then I mesh with a mesh length of 20. So actually every region is translated then into a mesh element. And a very regular measurement. Just a stupid trick to fix and to control or get my hands on how the mesher will create a certain mesh. And then it worked. I could do a quarter thing, and it took me 15 hours with a 3D model. And you see some kind of result here. But that, using the same methodology, but using the shell elements, I could even model a quarter of the gyroscope, because that is the opposite structure. And to solve that one, it took me 10 minutes. Now, then I was happy, and actually here's a comparison between the accuracy between the two simulation approaches. Less than 1%. I don't say that my accuracy towards the real device was less than 1%. Between 3D simulation and 2D simulation, that was enough. The advantage is, with this methodology, I can do 15 iterations on one day. Here I can do 2 or 3 iterations in 1 week. So you are far more efficient in the creative part, because you can try out several options once you found your path to come there. But it takes you a long time to get this. So, some conclusions. The success of MEMS simulation depends largely on the mesh, and that forces you to do special modeling, special drawing. So you need a flexible drawing tool, either 2D or 3D. An interface between this drawing tool and the simulator, so import, export, scripts or whatever. And the next question is how to cope with design changes. So every time that you want to change something in your layout editor, because people like to draw in their layout editor, redraw everything again, or make use of P-cells. So the gyroscope example demonstrates that my design is a creational phase and a verification, and actually how to verify was changed in how to mesh, and even how to mesh was changed in how to draw. So there's a lot of tedious drawing required. So in this loop, I will now focus my attention in this fast creation of geometries, and then next phase will be about fast verification. So how to automatize this thing? Okay, in the early days, people then, they made just a script, and in my case, I had a script. I did not draw directly in a GDS layout editor. I choose AutoCAD because it has my interface directly to the 3D measures. There are little finite element tools that have GDS import. So there is some format in between that I can go to my layout and go to whatever, in this case, ANSYS. I know groups, we work together with groups that had everything under program control. You can make a kind of sketch of the structure that you want to simulate. You parameterize everything, and then you have a script that makes a 3D model and apply boundary conditions and even the settings to solve. Now a lot of programs, they have, while you do something in the graphical user interface, it keeps a kind of log file, not the standard log file, but a log file that shows you the equivalent command to do what you do in the graphical user interface. And that was built in the old times to, let's say, in case the power stuff, that you could just rerun that log file and don't lose all your time. The nice thing is with that log file, and Console still has it, ANSYS has it also, I think Mark, I'm not sure, that is that you can then take that log file, and instead of the hard-coded length, you can change it into a variable, and you can read it, and you have a parameterized model. Now there is one problem, is that risk of collapsing geometry and setting loads and boundary conditions under program control is difficult. I want to illustrate this with this. Assume that I have this kind of comp, and your program internally puts typically numbers to the nodes and the faces and the edges. In this case, I just applied some numbers. But then I change a parameter to, let's say, change the width between the fingers, and you see that the structures, they move. Now what happens here is that this phase, initially these were 1, 2, 3 phases, numbered 1, 19 and 18. There is no 19 anymore. And what happens with 1 and 18, that completely depends, let's say, on your software tool. Now if you applied in your something at phase 18, a boundary condition, and you then run it with different variety parameters, you suddenly will see that there will be, in this case, a kind of permutation of the numbering scheme, and instead of applying your boundary to, let's say, even that phase, because of the permutation, it can happen here or can happen there. So that's what I call collapsing geometry. And okay, if you further move the distance, 19 appears again, but then you will constrain or have a electrical force on a completely different side. Okay, and that leads me to the question, how to apply. If you don't see it under program control, because with the graphical user interface you can do it nicely. To answer that, I will give it my opinion. First, some words about how other companies did it. Actually, what people did initially manually, make a script. In the early days there were actually from MIT, Coventer were formerly known as Microcosm and IntelliSense. Actually they came from the same group. They said, okay, let's implement a scheme that automatizes that. So you have your layout, you have a process description with the material properties. We provide you with some software tool that can automatically create a 3D model that can then be fed into a finite element solver. And actually that was the reason why these companies started up. Soft MEMS, early days it was from MEMSCAP, but it was then sold. And then if you want to parameterize it, you can start from a P-cell. That's a little bit what I call the IC design philosophy. It will become clear during the rest of the presentation. And you can see here examples for Coventerware. You have a 2D layout editor, you have your material properties, and the process description. It creates a 3D model where you can do the pre-processing, partitioning, transform operations, and then you can mesh it. The other company, IntelliSense, they have an equivalent layout editor. They have the project is called Clean Room, and actually it has the process description, and then it can generate from the 2D information with the cross-section information. You can make a 3D model that can then be meshed and solved into their finite element tool. And soft MEMS, they adopt a similar scheme. Some of them are built on existing tools, some of them completely programmed it. So in this case they use Edit. They have a technology manager which has the process description and it creates models for ANSYS. This is the PC-based version. They also have a Unix-based version, but then it's based on Cadence. They have a foundry process description, technology manager, and it creates actually a format which can be read in using ANSYS. There is a problem. Actually, from layout to 3D, that is automatized. Okay, it's already a good step, because you don't have to write the scripts yourself. But then in the preprocessor, you have to partition, you have to label the parts. Like in electronic schematic, you have to set the voltages on the nodes and give names to the pins. You have to measure it, apply loads and boundary conditions, set up the solver. But very often, during that part, there are problems. Your mesh is not correct, or you forgot something, and then you end up in this loop without results, and that is very boring, tedious. Most of these tools, they don't have a button. Even when they have an undo button and you are here and your mesh does not work and you have to come back to the layout, you have to redo everything. Imagine that an electronic designer, after every AC or whatever simulation, he has to rename all his ports and pins and set up the voltages again. I think he will not be happy, but that's still the case in this world. So, you make an error, you forgot something, or it does not work, so that's, you have to redo many of the things. actually during the training courses, the hands-on session in the Stimesi courses, I'm most of the time very happy when people do the tutorial, they have followed the course, and then they do the thing, and they, in some way they forgot something, and then the only thing I can say, okay, you have to start over again. After, let's say, 40 minutes of work, they have to redo, which supports my definition of the problem. And only when you get through the loop, you can become creative. Well, in the company I developed something myself, together with my colleagues, how to keep design freedom in layout and still have this automatized. From 2D to 3D, pre-processing solving under script control. Because if you make a P-cell, you know the coordinates of a certain face, and then on the script control you can select everything which is between those coordinates. But if you just have layout in a certain layer, the program does not know the X and Y coordinates where to select. And still we wanted to find the trick. And actually what we did, so how can the script select parts or faces from the geometry when you just have GDS? And the trick is, instead of drawing, let's say, masks or even layout that is for the foundry, a designer, he should forget about the process. Of course, he should know about the process, but he works in the functional part. So instead of drawing, let's say, my mechanical layer, my comps, my anchors, my spring, my mass, my holes, which all form parts of the same mask, just draw them in different layers. Because when they are different layers, you can treat them in your modeling tool differently, because these are the functional parts. So instead of drawing this, you have to draw that, every color in a different layer. You can later on go to tape out and do some layer mapping and so on. And mostly layer generation techniques which are built in these tools for DRC, you can use it to extract that even automatically. And then the procedure is the following: you can do visualization, process, materials, and then you import layer by layer. So you have your layout, and everything which is in one layer gets a name. So this is my mass. In ANSYS you can hide the object. In COMSOL not. COMSOL puts everything together. But if in COMSOL under program control, you can import layer by layer. But if you import first layer and then you have to move it to a coordinate 200,000. And then you import the next part, you name it, and you move it again to coordinate 200,000. So to separate everything, so some kind of tricks you have to know. So these are the different parts I import. And then I have my full structure. And then I can have a script that because parts are known, I can select my part, I can glue them together, I can apply a certain mass, I can mesh with a certain density. Of course, you have to be careful that if you do Boolean, you have to keep track, because your parts change, and you have to label them again. And that is maybe some tweaks you have to do, but still it's less than doing everything manually. And then, of course, all this, because your parts are known, you can, under program control, you can do a lot. And even with tools that do not offer you a lot of flexibility in undo and so on, under script control you can actually dump everything which is after this phase on a disk. You can dump it on this phase on disk. And actually the nice thing is you can develop separate subscripts, and if you are somewhere here in a test phase, you apply some more steps, and every time you try it out, it skips that, but then it loads the last disk. So it's incredibly fast. You can just test the last 3 steps and you see, oh, this is a good mesh, or no, I have to change a parameter, or I have to change a dimension. If you do something, of course it has to run. But if it's only on the last steps, and gradually you build up the full script, which can be reused next project. Maybe when I have time at the end, because I don't know how, I have to look at the time. I can demonstrate you this to a certain ANSYS model, and it's lightning fast. Even without user friendliness, you can do that. Okay. That's what let's say that's what we developed. I mentioned about this philosophy. There is another approach. Do not do yet, but I was collaborating with engineers which are using the typical 3D modeling CAD tools like ProEngineer, now called Creo, you have Katya, SolidWorks, SolidX, Rhinoceros. And actually, in the, let's say, the IC design, we have seen 20-30 years improvement in Cadence and Mentor and all the advanced tools, but related to visualization and organic growing of whatever models, they are a little bit behind. Of course, they are very performant in their schematic modeling. Go to the classical mechanical industry, they have developed something, they didn't stand still for 20 years. So they developed the constraint design approach, which I will address in a moment. But mostly you have some 3D solid modeler, and then you have an import directly to the FMA tool, and sometimes you have an export. But what they also have, of course you have to pay for it, is a bidirectional connection. And that is nice, because everything which you do here is directly known here. You parts, you give them a name, you give them material properties, and here you do, let's say, and then you do the simulation. Even if you rename it here, it is known there. If you have to change something, you go there, but you don't have to redo everything. I think it's valid to learn from this world for MEMS design. And it also allows, once you have come to a model, that your solver is driven in a parametric mode, and you can do Monte Carlo analysis or whatever, and you leave the solver run. Just a little bit further. This typically is the pre-programmed cell. Of course, in the IC we know how a transistor looks, and it is parameterized that if you have a longer gate or a bond path or whatever, then the number of vias increases. But in this world, a lot of things happen organically. You don't know exactly in the beginning of the project how it will look. So the creative phase is here on the schematic level, while it will be created on the layout. And constraint design is the following. Assume that you want to model this kind of flange, and there are underlying geometries. Somebody who will program that in a P-cell, he has to calculate the exact coordinates and can put that in a program. And he will have to program a code to solve for, let's say, to find this point, because it's a solution of two other lines. In a constraint design, I do not care about the exact coordinates. I say to the program, for example, this is the other here, sometimes it's exact radius, or sometimes it is important that that I can say that it is so much wider than the other one, and you say this on the same axis, and in this case I just say it's tangent. So I do not define exact absolute coordinates, but I define to the program how they relate to each other. With the advantage then, if you want to change certain dimension, so the undo function is actually built in, or even more important, I can change a parameter, and because the relations, it can build up the structure. Of course, you can do it in the wrong way, or there's also problems involved if you have conflicting constraints. But actually that solves you from making the P-cell. The program itself does the work for you for the absolute coordinates. So you can organically draw and still have a kind of parameterized geometry as a result. This shows you, but I have to look at the time. Well, I will quickly. It's a very unsharp video, but it shows you the power of mechanical CAD engineer. It's not speeded up, it's real time. They have, let's say, I work together with such a person, MEMS, not, but he made the other tooling. So drawing circles, but then afterwards you put the dimension, selecting edges so that you tell to the software that it's depending or ending on that certain phase. Okay, you can do the same thing in a normal 3D CAD program, like AutoCAD, but then it's fixed in shape, it's not yet parameterized. A little bit further, there's a nice example of this parameterization. So, okay, now here he will define a kind of round shape connection. Of course, he's working in a working plane, but then he selects this edge so that it stopped there. Then there is a kind of arc connected to that, but it's still not. Let's say the dimensions can be updated like is shown now, from that point to that point, and you see it updated. And also the width of that arc. So that's another approach. Which I just wanted to show you, to draw your attention to different approaches. So this brings me to what I call the difference between the ADA culture versus CAD culture. This puts a little bit the different things together. So this is what actually is MEMS using the IC design philosophy. Layout, process, material, make a 3D model, and you make a finite element model. This is MEMS design following, let's say, the typical mechanical. You directly model it in 3D, or maybe they have an intermediate 2D model for sketching. And depending on what you need. So I can imagine that if you are also facing the package and so on, that this can be more efficient than in this way. And this is the IC design because they are working on the schematic level. And there is an underlying parameterized model that allows you to solve, and there is an underlying P-cell that can give you the layout, which those people then also can make into a 3D model. And the current trend, and this is typically now for, let's say, tool, and IntelliSense, they are simple, is to extend this towards the IC design. This is the Lego brick approach, and let's say I don't want to say that it's not a good approach. It's a very efficient approach, but it will become clear why I call it Lego brick. So, okay, in this case, this is parameterized modeling Coventor. Originally, it was in Architect. So you had, of course, the materials. You have a certain process description, and in Architect you could put schematic blocks, connect them together with an underlying capacitor, and it's connected to L-beams, the supports, and actually, like in SPICE, you have hierarchical models. So actually, the L-beam is composed of two linear beams, but you have to define, let's say, not only the connection in electronics. By drawing a line, you force the voltage. In the mechanical world, you have to connect them, and you have also to say what the physical relation is. Some more equations you have to fill in, which is a little bit more tedious. The advantage is, once you have done that, you can go to Designer. It creates a 2D layout. You can go to 3D. This is another example of a more complex structure, and you have fast solving models to do this dynamic analysis. Now the difficulty is, in order to design this, I had to draw that, create a process flow, and go to many dialog box, and hope that the software understands what I wanted to model. Initially, there was not a 3D feedback, and I was simulating something with a gap of 3 microns, and I saw it in the graphs going 10 microns. You have to imagine, if you have a plate, let's say in electronics, you know the nodes and you can typically, but if you take the core, a lot of curves, but it's very difficult to interpret what is happening with this structure. Okay, they improved. They have their 3D visualizer included. Other software does the same. So for IntelliSense Simple, they have a schematic modeler. You can do the fast simulation. It generates layout which you can extract to 3D using the process description, and you can do the modeling. It's the same difficulty, in my opinion, and it really depends a little bit on your own preference. Some people that doing MEMS design prefer the style of a programmer or a schematic designer or layouter. It really depends on what you are skilled and what you challenge, and also in what you really want to model. Because this approach is also more tailored for lumped devices, and typically these mechanical SOI type of devices. But I think you are getting to problem already if you have a bulk mic machined device. There is an improvement, so this goes from Coventer, this MEMS Plus. You directly work in a 3D environment, and well, we deliver courses on that, but it's still sometimes tedious to make a correct working model. I'll come back to that also later, but this is the only thing that allows you to directly solve within Cadence these models. So for co-simulation, it is the only option. They extended that also to MATLAB Simulink since 1.5 years, and that is powerful. I'll come back to the co-simulation in a moment. Okay, I'll quickly go over this. So, to summarize, if you are in the phase of a top-down approach, your process is already known. For example, you're working on a fixed technology where there's a design kit available, so within Europractice or any other, let's say this is a PW service, you have CIC in Taiwan, you have CMP in Grenoble in France, so then, of course, you have a lot of this, you have this design kit, and you can start with layout, make a 3D model, and you can do it in that way. So that's maybe then the advised approach. In another way, or sometimes you're confronted, let's say, with initially some partial investigation. Do I have to make a process, a fake process flow, to only model a part of it? Sometimes it's then more efficient to start directly in your 3D model of your finite element tool. Or if you are in the bottom-up phase, there is already a device, but there are problems. Then you are confronted with you need to model it very accurately and with much more physics. You cannot just say, I'm only modeling the functional part. And then I think this approach is even better. For example, how would you otherwise model the round ball bonds and the underfill and so on using a kind of process description? It can be very complex. And then this approach, making use of these parameterized models like I've shown you with Simple and MEMS Plus, I think that is indeed only, let's say, the only which is at this time valid methodology to do co-simulations, especially for gyroscope. You have to really tune it and tweak it and test it. Model sharing, and also because it's fast. You can use it in the, let's say, in initial phase after your hand calculations to do some validations of some of your ideas. So I spoke about fast creation. That is the geometrical parameterization, fast verification. Let's say typically in single domain we don't need, let's say we can do finite element modeling or finite element analysis. If you have multiple domains, you have really to go to the finite element tools. There is a special case which is MEMS plus IC co-simulation. I already addressed the parameterized models. In the end of this presentation I will also address the reduced order model, actually, which is a kind of case which I already mentioned, supermodeling. Behavioral models like in MEMS Plus or Simple, and actually there are some teams like I know in a group in Italy. They are experts using Cadence MEMS models or what is spectrum models. What's that? Beam bars, like here. Okay. Let's look at co-simulation. And I start with the device level. Typically, you have a MEMS device and you have an interface IC. And actually, you have some information from the MEMS device to the interface IC, and sometimes, or mostly nowadays, you have a feedback or a control loop. And in the early days, how did we do co-simulation? You just didn't do co-simulation. Somebody designed this one, somebody designed that one, and they communicated using specifications. That was easy. For pressure sensors, you can specify the Wheatstone bridge, the maximum voltage, maximum temporal rise. But if your structures become more complex, how do you, for example, resonator? Well, actually, we have seen today equivalent electrical models of this kind of resonators. You can do some mathematics on this structure and derive an equivalent model, which you just plug into your IC design SPICE or Cadence. And then you can actually validate your electronics on that structure. And this is simple. You can extend it with dependent voltage sources and so on to also model the Pauline and the nonlinear effects. But still it is making use maybe of idealized properties or for simple geometries. In the case that your geometry is a little bit more difficult, you could, for example, and that was in the case with COMSOL. Actually, COMSOL was first, FEMLab was a toolbox within MATLAB. So therefore, they still have a good relation within each other. So with COMSOL, and nowadays you can still do it, you can make a finite element model and import it as an S function into Simulink, and then you can also add some electronic components like here. So this is the model in COMSOL, and it is an S function in Simulink, and Simulink, Simscape, now SimPower Mechanics, they offer also some electrical components. Or you have extra plugins that you can really import your SPICE into Simulink, but these are third-party softwares. And that allows you to do the co-simulation. And every iteration here, it does the simulation over the FEM domain in the loop, which is a restriction. So for simple geometries, and in this case a temperature model, for example, to just model heat control over structure, it can be done. But it's not a good solution for very large geometries, because the speed of the simulation is enormously reduced by going over the loop of the finite element domain for complex geometry. One solution was to go for a reduced order model. And actually what this does, okay, I come back to that later, is instead of having the finite element in the loop, you can reduce that model to a simpler model, which you can just then plug into a simulator. So instead of simulating that, I made a model. Let's say this was maybe order of 300,000 degrees of freedom. I can simulate it and reduce it to a 20 order model. So 20, a matrix of 20 by 20 or even 11 by 11. And then I can, following the same methodology, have some equivalent electronics and something which fits into Simulink, and I can do co-simulation. Which was, of course, a flow path that was adopted by this typical MEMS software tool, software vendors. Actually, SoftMEMS, they provide a tool that they generated from the ANSYS models, equivalent SPICE models. Coventor, they have a tool integrator that takes the finite element model and it calculates equivalent mass spring models or equivalent capacitance matrices so that it can be imported into Architect and then can be solved with, let's say, in this Sabre environment which I've shown you. IntelliSense, they also have a system model extractor. So they take away this work and they do it directly. Is it? I did not have an experience with those things. Sometimes it's limited to certain physics that you can reduce. And then the next step to do co-simulation is what I've discussed already, is making use of the behavior models that are provided by these software vendors. And then actually you more and more overlap these two worlds. So I mentioned Architect, Coventor, which runs into Sabre. That was the old version. Now with MEMS Plus it runs into Cadence and MATLAB. And there are also some other tools that you can find on the internet, or Modelica, or like I already told, some companies, they develop their own Verilog A inspector to do co-simulation. of their electronics with their MEMS. And the future, that's my hope. Maybe they will adopt both cultures and glue everything together, so that with MEMS Plus you can really, because with MEMS Plus you do not yet so you have a 3D geometry that you can see, but you still have to fill in a lot of dialog boxes. I want to do it completely geometrical, and under every block they could include a mesh that is automatically then. So let's say there's still a lot of things that can be done. So also hopefully your work will be lighter in the future. This brings me now to reduced order model. Why do I mention it? Well, one of the disadvantages of this, let's say the behavior models that are provided by the software vendors is that they are actually, you're limited to the blocks they deliver. We had, for example, at IMEC we also did some research on timing devices, and you have with Coventerware beam models with flexural freedom, so you can make flexural oscillators. But for a breathing mode, the building mode block was not provided, so you're blocked. Or in say architect models, they're mechanical, but they're also thermal models that really model heat transfer. The MEMS Plus, they only provide properties. Of course, there is some thermal effects modeled inside, but it's not full thermal simulations. So maybe they will introduce later on building blocks for that, but you're still limited. Last week I was on a workshop here in Chinchu, modeling the gyroscope. I draw the gyroscope, let's say the fingers in a certain way, and at the moment that I want to implement it, I saw, okay, the outer finger is different from the one I needed. So that's why I call it a Lego brick approach. If you are in need of a dedicated Lego brick to really mimic your motorcycle, you're blocked. But if the blocks are available for what you need, it's still the fastest, the most efficient way to do it. And again, you have to be careful also. You have to know what the building blocks models. Like in the case of the gyroscope, you can set up the frame as a rigid body, but you can also model it as a flexure body. It costs you a lot of more time to make it a flexural body. And in the end, maybe instead of making a geometry which you mesh into smaller parts, you start with building blocks to make a full structure, but your building blocks are becoming more smaller. In the end, you may be meshing with better models. The model order reduction technique is different, and I like it because it's generic, so you can apply it on any physics, but it has a disadvantage that it can not be applied on nonlinear systems, and it can only take a snapshot of the device, so it's not pattern-based. So, what is actually the workflow? Mostly you start with a partial differential equation, that is the physics, and actually the finite element modeling translates that in a set of ordinary differential equations. Now, that matrix we are going to reduce to make it faster, and then we can do the simulation. Maybe without going in too much detail. Okay, this is an example of the heat transfer. This is a partial differential equation, and in the finite element methodology it is translated into a matrix form. However, this does not define your input. Okay, it defines your inputs or the driving forces, but it does not define your output. Mostly in the finite element you can still rotate and see what the result is. But if I define what is my input specific, and I define what I want to have as an output, not information on all the nodes, but just on some positions of my structure, I can rewrite that structure in a state space representation. Allow to reduce the there's a kind of extra information that you have to give to the solver. I'm only interested in this input and that output, and then you can throw away a lot of information of overhead of degrees of freedom. Here is again this state space representation, and you see the same matrix appearing. And if you look at for a typical thermal simulation, These are typically sparse matrices. It's logical. If I have a huge structure and I have mesh here, the temperature of the elements on this element are of course only affected by the elements in the neighborhood and not of the elements there. So that's why typically for thermal problems you have a lot of zeros. It's not for all physics. Electromagnetics, there, something which happens there can influence directly all my elements. So you have to be careful about that. So typically you have a high order degree of freedom and we want to reduce that to a lower. This shows, if you're interested, kind of physical representation of where the, let's say, the diagonal and the off-diagonal. Of course, the off-diagonal are the relations between every node, and in this thermal system, these are the relations between the zero node and the other. But that's maybe not so important. Always sparse matrices, I just say no. You have to be careful with that. And what is now the purpose or the methodology? And that is just developed by some mathematicians. You have a system of order n, and this is actually, in this case, x is the set of nodal points, so the unknown on the nodes. If you can find a projection so that with a lower set of states you can calculate the full state, and then you fill in this equation, making use of that transformation, you can rewrite that a new set of equations but with a lower order. How it is done? Actually it matches, so it transforms the structure into the frequency space and try to approximate only in the frequency domain of your interest. Here it is graphically shown. So here this is your state space representation. This is actually the projection, so you have a smaller number of parameters or internal states, and you can calculate that, the full internal state, and you get a reduced order model. So that's already shown. Maybe I'm going too quick to this case is about ANSYS, but I will just with one example. This was an example of a microcalorimeter. Actually, what you do is you have some liquid here, you have liquid here. There's a thermocouple between both. Here is a chemical reaction, and we wanted to measure the temperature increase. This is a device with extremely scale differences. So it has a thickness of the membrane is 2 microns, but it consists of 11 layers, and in the length you have about 2 millimeters. So applying the good ratio of meshing, if you want to model it with solid meshes, we came out with, let's say, more than 6 billion of elements, if you just calculate easily. So it was not a solution, but by making use of shell elements, I can model it, let's say, more easily. It represents the thickness of the 11 layers, and I could mesh. This is the mesh, no, this is the partitioning, and this is the mesh. And actually I could then in that case already have a full row, because I wanted on the full wafer scale see the effect of several cells on each other. I could do the simulation. Here is a quick example of such a transient simulation. It's nothing special visually, but you see that the temperature goes away, and you can calculate from that. Now, that was the first step, let's say the optimal meshing. The next step was actually to reduce, to make a reduced order model, and in this case it was a very low order model, even of order 11 I think, and this compares the results of the full finite element simulation and of the other one. The nice thing is you can play with the inputs now, as long as your model is linear. You also see that in the transient here there is a mismatch. That's because the Taylor serial expression was driven to converge around zero frequency, so the steady state, that was more accurately represented. There is okay, what is the power? It is generic. You can apply it for all this physics, depend on the building blocks of whatever. So that's the nice thing. But it's not parameterized, it's a snapshot. So if you are in the co-simulation work, you can make your finite element model. It just costs you one static simulation, But then you can give this state space representation, which you can translate into SPICE to your electronic designer, but you have to inform him what parameters he can apply, or what voltage or whatever. And if he needs to make a change in the dimension, then you have to do the process again and give him another dimension device. Here's another example of this timing device. I'm going to quickly over it because there was a nonlinear effect in it. So actually, if I have let's say a current of 1 amp through it and I see a response, doubling the current would make the power 4 times larger. But if I include that in my reduced order modeling, my reduced order model will just assume that the power is doubled. But you can split out the nonlinear effect, and in this case we just applied a certain continuous Joule heating to the structure. Instead of applying the current, it was validated first in the finite element mode. We did the order reduction, and here is some graph. In this case it was only with 1 input, and you see there's a kind of difference in ambient temperature. The dots are the full simulation, the lines are the reduced order model simulation. And here is a difference between both, and on a range of, let's say, between -40 and 100 degrees, you see that the error is between 0.1 and -0.2, so it's less than 0.5% accuracy. For the transient, for the steady state, it's even more. So you see the power that you see with an order of, I think, 20 or 30, it's like instantaneously that you see it, while the full anti-simulation, it took 2 hours. There are some tricks to add more inputs, and in this case there was another input, so we could also model the ambient temperature. Well, it just shows you that it works. So, to conclude, there's a lot of creational. You can do it parameterized, you can use a constraint approach from the CAD, or you can make scripts. Verification, this is typically known by the people that are doing finite element simulation. I spoke about the special case of co-simulation. The other verification is the design exploration and DRC. That's what we also normally cover during these Stimesi courses, because you can do a lot with DRC also. Not only checking whether if this structure can be processed, but you can also derive other things. But this is the end of my presentation. I want to conclude. The data is typically in the design kit. There are many tools, but no tool can do it all. And the methods, that actually is the important thing. Sometimes you need to develop a kind of structured approach. And one of the things is known design paths. So it's very difficult to predict how long it will take to get something ready, because you spend most of the time first in path finding. So the managers, they come to you and they say, okay, we have a customer, can you design this? But if this is a physical problem that I never have solved, it's very difficult to predict that. So the time, and like you've seen, sometimes you spend even 2 months in developing the path, and only once you reach the first result, then you can be creative. So there is a lot of know-how. Best thing is to document it, but the most important thing is that it's in the people's mind, in the head, and that's I always say to my manager and to the team, say, invest in the people. Thank you for your attention. I don't know how much I'm over time because they forgot to start the clock. If you're still interested, I can show you this analysis quickly. Is that time? Or do I? No, it's finished? Or